Good afternoon. We are back. Mastering Diagnostics, video number 12. Can you believe it's 12 already? Time's flying by. I'm Brandon Steckler, technical editor of Motor Age Magazine, and this is going to be video number 3 in my little mini series I call Learning How to Learn. So we implemented some tools to discover faults based around spark or ignition faults. And then we did the same regarding the fuel injection system. Now we're going to focus on engine mechanical integrity. And you all have seen me perform tests like this before, specifically the relative compression test. But what I'm going to do is I'm going to show you how to carry out that process live on a vehicle. And we are going to do it when the vehicle is healthy, first and foremost. And what that's going to do is allow us to establish proper operation of the lab scope, meaning proper implementation as well. We've all been down that road before. You see something demonstrated in class or in a PowerPoint presentation, and we're all excited, and we get back to the shop and we go to do the test, and we can't get those test results to end up on our lab scope screen or on our scan tool screen the way it looks so easy in class. So working on known good vehicles that don't have a fault currently, is what you need to do to get started off on the right foot. Because if things don't appear on the screen as you expect them to, chances are you're making a mistake. You don't have the tool set up correctly, something of that nature. However, if you're working on a car that's broken, you really don't know if what you're seeing on the screen or lack thereof is because you screwed up or there's something wrong with the car. So always, 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 always start on a known good vehicle till you get comfortable with the test and you can prove to yourself that you're using the tool correctly, you're performing the test correctly, and you are acquiring the data correctly. Then's the fun part. After that, and we capture that information, we're going to store it on the lab scope. We're going to come back to my desk and analyze it later. We are going to implement a fault. That's right. We're going to remove one spark plug from this 6-cylinder engine, and we're going to repeat the relative compression capture. And if all goes well, what we're hoping to see is not only that a fault is indicated, but because we're going to be using an ignition sync, we'll discuss that in some detail coming up, an ignition sync, and I'm going to pre-research the firing order so that I know the enemy. I know what I'm working on, and I'm familiar with it. When I have the firing order and an ignition sync, I can tell which of those 6 cylinders is low on compression. So it's one thing to implement a relative compression test and discover really, really quickly, I mean within 30 seconds, whether or not you have a cylinder that lacks compression. That's one thing, and that's a great thing to accomplish. But if you can take just a couple more minutes to implement a secondary ignition sync or a primary ignition sync or an ignition command to a cop coil, and you research the firing order, again, another 2 minutes. 2 minutes of your time is all I'm asking for. You can then pinpoint which of those cylinders is dead. Okay, so why is that a big deal? Well, it's a big deal if you're working on some big V10 Ford Carpenter van. And if you're anything like me, you're just over 5 foot. So if I got to reach into that engine compartment, either underneath the hood or through the dog box, I got to get somebody to hold my ankles so I don't fall in. And that takes a while. So being able to implement a relative compression test will save you a bunch of time. Like I said, don't take my word for it. Let's head out to the car and we can see how this is carried out. Before we actually head out to the car, we have to do some research. I'm utilizing MotoLogic repair and diagnostics system today. Try something different. And what I like about MotoLogic is the hyperlinks. So it really makes things very similar to factory service information. In particular, what I'm going to strategize to use is the keyword search bar. So I'm going to type in firing order. And what I'm looking to find out is, first of all, cylinder configuration, which tells me how the engine is laid out, because not every engine alternates 1, 2, 3, 4, 5, and 6 from bank to bank. For instance, Honda carries cylinders 1, 2, and 3 in the rear bank, the one against the firewall, and cylinders 4, 5, and 6 up near the radiator, whereas other engines would be 1, 3, and 5 in the back and 2, 4, and 6 in the front. Excuse me. So this is going to be labeled as follows. We are going to be referencing ignition cable number 6, and the firing order is 1, 4, 2, 5, 3, 6. So this is really going to serve us well. And again, I don't memorize this stuff. It does not pay to memorize this stuff because there is 31 different firing orders used today. And to make a mistake could mean removing the wrong cylinder head due to a misdiagnosis. So now it's safe to head out to the car since we know the firing order and we know the cylinder position.
So we're out at the car. As promised, I'm going to flip this around so you can see what's going on. So, pardon the light there, that's going to help us see. So what we've got here, if you recall, we've got a waste spark system, which means we've got 6 outputs going to 3 coils, and that's located way back underneath the cowl panel, so we're not going to worry about that. However, we are going to use this secondary pickup lead, as I discussed earlier, in front of the computer. That's going to allow us to grab the energy capacitively flowing through these wires. So I'm going to reach down here and connect it to one of the wires. It doesn't matter which one, as long as I know which one it is. Just like that. Get a better view of that. See if I can zoom in. Boy, this is tough. So, there we go. Right around the wire. And what's very important is connected to this is a ground lead. Now this ground lead should reference ground. I like to go right to the battery, but you can go to anywhere that's grounded. What that does is it prevents any discharge that might occur at the wire from traveling up this lead and going into the scope. So we've got that connected to channel 1. Channel 2 is my trusty amp probe. The amp probe is going to get connected around the battery starter wire. So the heavy wire going down to the starter. This wire feeds the fuse box. One of these wires comes from the alternator and the other one goes down to the starter. Since the alternator isn't charging while we're cranking, it really is not going to cancel anything out. Now, I want to point something out here. You'll notice the amp probe has an arrow. That arrow is biased, should be biased towards current flow. So since electrical current leaves the battery here at the positive post and makes its way down to the starter, we're going to connect it just like that. And be sure that the jaws are closed. I will set this over here on the 2000 amp setting because 200 amps is not enough for starter current. Now it's time to come over here and set up our scope. And what I'm going to do, pardon the glare, this is really hard to do with one hand. We're going to come over here to channel 1 and we are going to choose our probe. Now our probe, let me zoom in a bit more. Our probe is going to be our amp probe, the one going around the starter. So we are going to choose the 2000 amp probe and on the 2000 amp setting. And then we are going to set our channel up. The range here, right now it's reading plus or minus 200 amps, so 0 is in the middle. It can read up to 200 amps or down to negative 200 amps, 200 amps in the other direction. That will not suffice. So what we're going to have to do is change it so we get about 1,000 amps on the screen. I know that because of experience. And when you start to mess around with good vehicles, you learn these things over time. So I know you can't see what I'm doing on the screen here, but I'm just going to walk you through it. On channel B, which would be our red channel, we are going to choose a probe. And this is going to be our secondary ignition probe, which would be right there. And we are not sure if it's positive or negative. We'll leave it on negative. Either way, it doesn't matter. It's simply going to present upside down on the screen if we choose the wrong one. We are simply using the secondary ignition trace as a means of synchronization, meaning we want to know when a specific cylinder is firing so we can then identify all the cylinders in the relative compression trace in the firing order, in the appropriate firing order. And I will leave that at a range of, let's say, -5 to 20 kilovolts. I am going to set my scope time base for 10 seconds on the screen. So since there are 10 divisions across the scope screen, 1 second per division is what I am going to choose. And what you'll see is when I start the scope, you will see it progresses, and it will take 10 seconds to progress across the screen. So, since the scope is running, I'm going to head over to the driver's seat, and we are going to crank the engine over. Now, fortunately for me, this older vehicle utilizes a strategy called clear flood mode. And what clear flood mode is going to allow me to do is depress the accelerator to the floor, because the throttle position sensor is reporting a high angle to the PCM. The PCM realizes I am requesting clear flood mode. And what that'll do is it'll allow me to crank the engine, but the PCM will not fire the fuel injectors. Again, that's great news, because we can crank and crank and crank, and the engine won't start. Other vehicles require a bit more effort to disable. Some of them you can pull a fuse. Some of them you can't, because the fuse that disables the fuel injectors might also disable ignition, or might also disable the PCM's ability to communicate. So the engine won't start, but then again you will lose your form of synchronization. Other vehicles will allow you to use scan tool bidirectional control to cancel the injectors without creating any DTCs. So I'm going to depress the pedal to the floor and crank the engine over, and we are going to listen. All right, let's stop the scope and see what we got. All right, so I stopped the scope screen. Let me show you. Here's waveform 5 of 6, so let me go back. Here's waveform 1. This was us in the car, me running my mouth, not doing anything. And then, here's waveform 2, much of the same. Waveform 3, much of the same. Waveform 4 is where I started to crank the engine. So, we're going to cover all this when I sit down at my computer. I just want to show you that it is on the scope screen, captured, and we don't have to be here to push buttons. We can let the power of the scope capture it internal inside the computer's buffer. So here's the relative compression amperage trace from the battery, and here is the secondary ignition capacitive waveform captured from number 6. And as I mentioned earlier, waste spark system. So look, high, low, high, low. All the high ones are the ignition coil firing under the compression stroke, and all the low ones are the ignition coil firing under the exhaust stroke. So here's waveform 4 of 6. This would be waveform 5, so we're just letting the key go here, and that's what's left over. So again, I'm just trying to show you that the scope really does store this stuff. I've got all this saved. We're going to analyze this in detail later. Now, the benefit of doing what we're doing is to experiment. We're working on a known good car, and we are going to create our own fault. As you can see, by capturing the data the way we did initially, it proves a couple of things. A, it proves we know how to use the tools. It proves the tools function, meaning the scope can capture, the amp probe can output, and the secondary ignition capacitive probe can create an output as well. Since we successfully captured that and we can visibly see that the car is in good working condition, it's time to introduce an experiment. What is the purpose of introducing an experiment? The experiment is going to allow us to be in control of a situation. Since I get to create the fault, I already know what's wrong with the car when I create that fault. Hopefully, the data capture is going to reflect the fault I created. So now the fun part. I'm going to remove a spark plug, and I'm going to re-perform the same test we just did when the spark plug was installed, and the engine was cranking over normally with no mechanical faults whatsoever. Think about this. What's this going to recreate? If I remove a spark plug, what is going to happen to compression in that cylinder that I took the spark plug out of? Compression's going to drop. Why? Because there's a big friggin' hole on top of the piston. All the compression that would be there is escaping out the spark plug hole. Let's think this through. What is that going to do to load on the starter? The mechanical load on the starter is going to reduce at the point when this cylinder is on top that center of the compression stroke, which of course would reduce current flow and should cause our relative compression peak to appear significantly lower than the other 5 in this engine's configuration. So I'm going to remove the spark plug and we're going to repeat the test. I've got the spark plug removed. Right here for cylinder number 4. So let's go inside and repeat the test. And what I want you to do is I want you to listen. I want you to listen with your ears as I crank the engine over. And listen to the audible characteristic of 1 dead hole out of 6. The best tool a technician has is the one between his ears, including his ears. So it's always a benefit to capture or to have an idea of an engine mechanical fault before we even start working on the vehicle. So we're going to walk over to the vehicle now, driver's seat now, crank the engine over to repeat that relative compression test in clear flood mode, and I want you to listen. At the same time, I'm going to turn the scope on and it's going to start capturing data. So we'll head over to the vehicle now. Get situated here. And I'm going to take the accelerator pedal and push it to the floor. And I'm going to crank the engine over and I want you to listen. Listen, before the engine starts. That's what we're after, the sound of that dead hole. Now let's go find out what it is. All right, we're back out underneath the hood, and I just want to show you this. We've got our capture, our relative compression trace. We're showing our dead hole here, and our dead hole there, and our ignition sink. So we're going to head back inside and analyze the data to see if our experiment showed us exactly what we expected to see. Because again, we created the fault. That's the benefit of either working on known good cars or taking control of the situation. We've removed cylinder number 4's spark plug. We've synced to ignition number 6. And the firing order is 142536. So like I said, let's go back to the drawing board and really pick this apart and see if we've learned this technique properly.
Okay, so we've got the known good relative compression capture on the screen here. This is where I hit the key and current began to flow through the battery cable past our amp probe. And what we can see here, now I'm going to zoom in. Let me clean this up a little bit. By getting rid of some of that, by filtering, I got rid of some of the noise. We can see that every relative compression peak is basically of the same amplitude, indicating all 6 cylinders, 1, 2, 3, 4, 5, 6 cylinders have the same amount of mechanical load on the starter. I do want to point out this ignition strike, if you recall, is from cylinder number 6. And the firing order is 142536. So this would be number 6 relative compression peak. And this would be 1, 4, 2, 5, 3, and 6 again. So now we're going to launch our faulted capture and take a look and see what's different. Hopefully our faulted capture will indicate number 4 relative compression peak. Again, 6, 1, 4, 2, 5, 3, and 6 again. So this one here, number 4, we should anticipate the third one in this firing order here to be lower, significantly lower than the other 5. If that's the case, then we've done our job correctly. Okay, so we're back on screen again, this time with the faulted capture, and I can already tell this looks very promising. So again, once again, I hit the key. The engine begins to crank. This is cylinder number 6 firing event, ignition firing event. Again, a whole engine cycle later, and again. So I'm going to zoom in on these 2 engine cycles right here. And I am seeing some promising stuff. So once again, I'm going to filter this just to clean it up. Not that is entirely necessary, but I'm going to do it just to make a little bit of a prettier picture for you. We get rid of some of that noise. Now again, the firing order is 142536, and our ignition strike is here on number 6. So 6, 1. 4 is missing. 2, 5, 3, 6, 1, 4, 2, 5, 3, 6. So we've proven that we had the tool connected correctly. We've proven that we've identified the cylinder correctly because when we removed cylinder number 4 spark plug, it created this lacking relative compression peak. I'll tell you what, that was a ton of fun, wasn't it? I mean, especially if you're seeing it for the first time. Now, I tried to go slow and I tried to show you my process as far as hanging onto the camera and clicking on the computer screen. But you gotta cut me some slack because I can't walk and chew gum at the same time. I'm just that topic. But my point is, it takes just a little bit of practice. Practicing with the tool you have, practicing implementing the tool on the vehicle, practicing the research, locating the firing order and the ignition system configuration so we can locate a sink. And once you do that several times, it becomes second nature. It becomes easy to perform. And you will find that these easy to perform tests that seem so advanced when you first see them, they're going to start replacing those hard to perform tests, the ones that take people sometimes over an hour to perform a compression test on all the cylinders because of how many cylinders there are, how rusted things are, how worn out things are, and accessing those components for removal. So again, I'm Brandon Steckler, technical editor of Motor Age Magazine, and I really appreciate you joining me on this episode of Mastering Diagnostics number 12, and we will see you next time.